it's my pleasure to introduce Matthew Loader. So he's a researcher assistant at the Lode Lab, Natural History Museum in London since 2017. And his research focuses on the petrology and chemistry of minerals associated with porphyry copper deposits and the implications for the assessment of ore forming potential in arc magmatic systems. He holds a master's degree from the University of Bristol and a PhD from the Imperial College of London. So Matt, we can go ahead.
Great. Well, thank you very much, Halleluya and Marta. Thank you so much for inviting me to give this talk today. It's a real pleasure to be the season finale, last but not least. So I want to talk to you today about my research, which Marta's introduced there. I'm interested primarily in mineral chemistry. I'm an igneous petrologist by background. And I've been working for the last, nearly 10 years now on the mineral chemistry of minerals associated with porphyry copper deposits. And the long-term aim of this work is firstly to understand more about from the mineral chemistry about the ways in which the magmas associated with porphyry copper deposits are different to any other arc magma or post-subduction magma that exists. But also another goal of this is to see whether there is any unique signatures, any interesting information in the chemistry of certain minerals in porphyry deposits, which could be used in exploration. So are there any signatures which our friends in exploration can use? And today I'm going to be talking about two minerals in particular. So they are Zircon and Apatite, and they're two minerals that I've focused on in my PhD and my postdoc since. So I can have the next slide, please, Marta. Okay, so the first thing I just want to briefly talk about accessory minerals in igneous rocks and what they actually can tell us. So accessory minerals, as you'll be aware, are minerals that are present in only very small abundances, not like plagioclase or clinopyroxene or amphibole or anything like that. We're talking about things like zircon and titanite and apatite that are typically present in abundances of 1% or less. And accessory minerals have a really interesting part in our understanding of igneous systems and other systems as well, including metamorphic and hydrothermal systems. They have they often crystallize quite late in magmas, and so there's a long magmatic prehistory before they crystallize, but they capture the kind of final stages of magma crystallization in general. And I have an example here from the Este porphyry in Chuquicamata, where you can see an assemblage of accessory minerals all together. So we have some large titanite crystals. In the dotted line there, outlined is a zircon, which you don't always see in thin section because they are especially rare. And there's also some apatite and magmatite in there as well. So these minerals all crystallizing together have the potential to reflect something about the chemistry of the liquid from which they crystallized, but they also have an impact on each other. The co-crystallization of these various phases impacts on the other phases as well. And that's an important theme, I think, of, of my research. Next slide, please. So just a bit of background about what we think, the way that we think that magmas, in arc settings and also in porphyry systems, the way that we think they form. So I kind of think of this as two separate stages, kind of a polybaric crystallization in the lower crust, in the deep crust and in the shallow crust. In reality, it's probably more of a continuum, a multibaric, I suppose polybaric is also fine, crystallization that goes throughout the crust, but I'm going to think of it in terms of deep crust and shallow crust just for the purposes of this talk. In the deep crust, we have the injection of mantle-derived basalts usually, and those basalts, they fractionally crystallize. In certain cases, if there's not a lot of water, they fractionally crystallize phases like plagioclase and amphibole, and that gives you a particular signature to the magmas that are generated. If we have a higher water content at higher pressure, then we crystallize things like amphibole and garnet. And amphibole is very fond of elements like yttrium, whereas plagioclase is fond of elements like strontium. And so whether or not we crystallize amphibole or garnet or plagioclase and the abundances of those phases affects things like the strontium-yttrium ratio of the magma that we generate by this deep crustal fractionation process. And so that's very often you hear when people talk about porphyry magmas and porphyry fertility, ratios like strontium-yttrium often crop up. And that's the reason, because they're tracking a deep crustal process where we grow crystals and we physically separate them from the liquids to drive the fractionation of those liquids. We're fundamentally changing the bulk magma chemistry. And then those magmas, they will ascend into the shallow crust, whereupon they will stall at some level and they will continue to cool. And in such an environment, we'll grow some more crystals. But the rules are a little bit different once we reach the shallow crust. Up in the shallow crust, it's much harder to physically remove crystals from liquids. So we're probably not doing an awful lot of fractional crystallization in the shallow crust. In other words, the chemistry that we make in the deep crust, the high strontium yttrium or low strontium yttrium, whatever it might be, when these melts, these magmas ascend into the shallow crust, that's mostly, with a couple of exceptions, that's mostly locked in place. And what happens is then this bulk magma chemistry that's in the shallow crust, as we generate more and more crystals and we have an ever dwindling pool of liquid that our crystals can grow from, we're causing the melt chemistry, the residual melt chemistry that's getting less and less, its composition will diverge from the bulk magma chemistry, which, as I say, is largely controlled by processes that have already happened in the deep crust. And so this has quite important implications for understanding the chemistry of crystals that we have in rocks, because most of those crystals, with some exceptions, are probably crystallizing in that shallow crustal environment, which means that they have the opportunity to reflect the bulk magma chemistry, which is, as I say, was generated in the deep crust, but also they can record this evolving and changing melt chemistry, which the bulk rocks don't see. You don't see that in bulk rocks. And obviously it should go without saying, I suppose, for an audience like this, the porphyry deposits themselves form in these shallow crustal environments, in the top parts of plutons and dike swarms associated with these shallow crustal intrusions. So that's an important thing to keep in mind when interpreting mineral chemistry. Next slide, please. So I said I'd talk about two minerals, zircon and apatite. So I'll start with zircon because that's the one I've probably done the most work on. So zircon in any magmatic setting has a couple of characteristics that are worth noting, and that is it has a suite of rare earth elements from lanthanum all the way to lutetium. The heavy rare earth elements like lutetium and ytterbium, they are present in higher concentrations and they gradually decrease as you get to the light rare earths like lanthanum. So there's a general trend in zircon chemistry of becoming more enriched in rare earths as you get to the heavier rare earths. And then there are these two exceptions, and they are europium, which is a middle rare earth, and cerium, which is a light rare earth. And I won't go into the details too much, I suppose, but we know that the europium and cerium have anomalous concentrations in most zircons from any setting. In general, europium is present in lower concentrations than we would expect, considering the neighboring rare earth elements, which are samarium and gadolinium. So we have lower europium than we would expect. And cerium is present in much, much higher abundances, higher than you would expect, given that the light rare earths are so depleted in zircon. So we call these the europium anomaly and the cerium anomaly. And we can express these europium anomalies in a few different ways. The most popular way is to do this europium over europium star ratio. Europium star is the amount of europium we would expect to be there if it was behaving like all of the other rare earths. And so because europium is usually less than this value europium star, it's usually a value less than 1. The ratio is a value less than 1. Whereas conversely, cerium is much higher than you would expect. So it has cerium over cerium star has a value usually higher than 1. Now, for various reasons that I won't go into, cerium over cerium star is quite a difficult ratio to calculate. It's mostly because the neighboring rare earths that you would use to calculate it are present in such low abundances, they're actually difficult to analyze accurately. So people have used other ratios, like the cerium-neodymium ratio is basically a proxy for the cerium anomaly in zircon. And in porphyry systems, we know that these cerium and europium anomalies that exist in zircon exist in their difference of what you find in typical kind of quote unquote infertile or barren arc magmas. So you tend to have in porphyry systems, zircons have higher values of europium over europium star and higher values of cerium over cerium star. And there's the results from 2 studies there, which have a compilation of zircons from barren and fertile systems. And you can see that that's the case. Europium star is higher, cerium star is higher, or cerium over neodymium is also higher. And so this is kind of another representation of what I was just talking about here. These are some chondrite normalized zircon trace element patterns, rare earth patterns, from 2 different systems. So from the Batu Hijau porphyry on the left-hand side, and from the Bishop Tuff, which is a barren volcanic system. on the right-hand side, and you can see that they have this increase in concentration of rare earths as you go from lanthanum to lutetium, so lighter heavy rare earths. And yeah, that's relative to chondrite. But then you see this anomalous europium and cerium, and it's easier to see europium in this plot. You can see the bishop stuff has a very negative europium anomaly. That means europium is much lower than we would expect. Whereas in the porphyry system, there's basically no europium anomaly at all. So that would be a europium over europium star value, approximately 1, something like that. So that's what we know about zircon rare earth patterns and the differences between porphyry and non-porphyry zircons. Now, the big question and the question of my research is why that's the case. So we can maybe use this as a tool for exploration, but what's actually driving this difference? So one thing that we've known for a few years now is that the magnitude of the europium and the cerium anomaly is sensitive to the oxidation state of the magma from which that zircon is crystallizing. And the reasons for that, the reasons we have cerium and europium anomalies at all, is because although the rare earths exist primarily or almost exclusively in terrestrial magmas in a 3+ oxidation state, so they're trivalent cations, europium and cerium are different. They can also exist in a 2+ cation, europium 2+, and that's the case of europium, and cerium can exist as a 4+ cation. Now, europium 2+ is really incompatible in zircon. Zircon hates europium 2+. So if there's any europium 2+ in the melt, then it's just zircon can't absorb that, and that's why you end up with a negative europium anomaly, because there's some europium that just won't go into zircon. And conversely, zircon absolutely loves cerium 4+. So if there's any cerium 4+ in the magma, then it will go preferentially into zircon. That's because cerium 4+ is so similar to zirconium 4+ in terms of its charge and its ionic radius. Now, if you change the ratio of cerium 4+ to cerium 3+, or europium 3+ to europium 2+, you change the ratio of those things in the melt, in the silicate liquid, then obviously you change the overall partitioning of europium and cerium. If you have a lot more oxidized europium 3+, then you have, you basically don't get a europium anomaly. And if you have a lot more oxidized cerium 4+, then you end up with a much bigger positive cerium anomaly. And that was demonstrated in some experiments that I've shown here by Anthony Burnham and Andrew Berry. And they grew zircons in the lab just up the road from here at Imperial College. And they did so at a range of oxidation states. And they showed that the oxidation state, as you go from FMQ minus 7.7, so that's very reduced, up to FMQ plus 6, that's very oxidized, you can see that the europium anomaly all but disappears. And the cerium anomaly goes from not existent to a big positive cerium anomaly. So we know these anomalies are related to changes in oxidation state. So what's controlling these europium and cerium anomalies? Is it oxidation? And is there anything that zircon can tell us about porphyry exploration? Those are the two questions I want to focus on. So many of you who've worked on zircon will know this famous study by Julian Ballard in 2001. He did his PhD in 2002, he published his paper. And what he showed was in successive intrusions at the Chuquicamata porphyry deposit in Chile, if you look at the zircons from successive intrusions leading up to mineralization, the magnitude of the europium anomaly, as I've shown here, and the cerium anomaly actually increases as you get closer and closer to mineralization. So from about 43 million years to 34 million years-ish, when mineralization took place, that europium anomaly in zircon creeps up gradually. And what Ballard and co-authors interpreted this to reflect was a change in oxidation state, going from more reduced earlier on to gradually becoming more oxidized as you get close to the period of mineralization. And this is important because the more oxidized you are, that has an impact on the speciation of sulfur in the melt. And it determines whether or not you have sulfide saturation, which can absorb lots of copper and metals and concentrate them somewhere in the crust that you don't want them, or you have predominantly sulfate, which is more soluble in magmas, and therefore you can have higher sulfur contents and you don't lose copper. So there's a metallogenic significance to being more oxidized or more reduced, as I'll talk about later. But what actually Ballard didn't show in his paper is that the zircon chemistry is also reflecting the rock chemistry. So here on the top right here, I have the same plot, so the same rocks, but this time instead of zircon chemistry, it's rock chemistry. So you can see that the europium anomaly in the rock chemistry is actually doing the same thing that the europium anomaly in the zircon chemistry chemistry is doing. And also, if you look at the plot below that, the silica content, that's also changing as a function of time. So as you get younger, you're actually getting more evolved magmas. So Ballard's interpretation is that the europium anomaly is reflecting oxidation state. But clearly, there's something else going on here. It's also reflecting the bulk rock chemistry. That's worth noting. And these are some modeling results from a mine at the Natural History Museum, Chetan Nathwani. And he showed really nicely and convincingly, using some experimentally determined europium partitioning models, he showed that actually the one thing that really controls the zircon europium anomaly is actually the melt europium anomaly. So you can see in this plot here, this is the results of a Monte Carlo simulation that Chetan ran. And he varied the melt concentration, the melt europium anomaly between sort of, I guess, 0.1 and 1.2. And he varied a few other parameters as well, including oxidation state and the little optical basicity there, which is a measure of how polymerized the melt is. And he also varied temperature as well. And what he showed quite convincingly here, I think, is that the one parameter which is really affecting the europium anomaly in zircon is the melt europium anomaly. So this is going back to the previous point I made about the Chuquicamata data, is that the rock chemistry and the melt chemistry have a very large impact on the zircon europium anomaly. Essentially, they're a big controlling factor, more so than many people would give them credit for. And the reason for that there is basically due to this equation here. So the europium anomaly in zircon is equal to the europium anomaly in the melt multiplied by the ratio of the partition coefficients for europium and europium star. It doesn't really exist as an element, but we can still estimate a partition coefficient for it. And as you get to more oxidizing conditions, and arc magmas are generally quite oxidizing anyway, the value of D europium total comes to be quite similar to the value of D europium star. What that means is that ratio of partition coefficients becomes 1 or very close to 1. And that essentially means that the europium anomaly in zircon equals the europium anomaly in the melt for very, very oxidized systems. It seems as though in porphyry magmas and other oxidizing conditions, the main control on europium anomaly seems to be the melt chemistry, the melt europium anomaly. And so this is something that I'd argued in the past in a paper a few years ago now, looking at zircons from Oyu Tolgoi, a porphyry copper gold deposit in Mongolia, where I did my PhD. And you can see here I have the europium anomaly in zircon on the left-hand side, the plot, europium anomaly in zircon versus the ratio of a heavy rare earth to a middle rare earth in this case. And what we argued in this paper was that these very high values of europium star, which would previously have been interpreted as reflecting oxidized conditions, can actually be generated by just crystallizing a very, very small amount of the mineral titanite. So when you co-crystallize titanite, it can have a very profound effect on the melt chemistry. One of those effects is that it increases the magnitude of the melt europium star. And as I just showed from Chetan's work earlier, in a relatively oxidizing magma, by increasing the melt europium star, you increase the zircon europium star. And that's kind of what we argued here with titanite. So there's a change in the europium anomaly that's not reflecting oxidation state, but it is reflecting the co-crystallization of another phase, in this case, titanite. And you can see this in one particular grain here. So I have a core that has a very boring europium anomaly, so 0.37, that's nothing too interesting. And then a europium star value of 0.75 in the rim of that grain, which is quite high. And you can see that rim is also associated with a very small titanite inclusion. So we have physical evidence there of titanite co-crystallizing with zircon, and also the effect that has on the europium anomaly. So I have to shamelessly plug some of my own work. Well, if I don't plug it, no one else will. We have a very recent paper that's just come out in Geochemical, and it's looking at the controls on the magnitude of cerium anomalies in zircon. I'd highly recommend you check that out. Of course, I would. So I'd sort of talk about some of the main findings from that paper now. And it's all about, cerium anomalies in zircon, the effects, the controls on them. So in this case, we had zircons from Resolution copper moly deposit in Arizona. It's a super giant copper moly, very high grade copper moly deposit in the Laramide of Arizona. And if you look at the bottom left-hand plot here, again, we have the cerium anomaly. We're using the cerium over neodymium ratio as a proxy for the cerium anomaly in zircon. And we've calculated temperature in zircon by using the I forget the exact thermometer we use, but there's a titanium and zircon temperature, a Ferri and Watson, I imagine. And you can see that as the zircon crystallization progresses, as temperature decreases, you can see the magnitude of the cerium anomaly increases significantly by about nearly an order of magnitude, in fact, an order of magnitude. Now, a previous interpretation of this would have been that in these particular magmas, as they cooled, the increase in cerium anomaly is reflecting a change in the oxidation state, as I say. But actually, if you look at the plots on the right-hand side for the same data, you can see the big change is actually the neodymium concentration, which is coming down. And that's unaffected by oxidation state. A decrease in neodymium is not reflecting any change in oxidation state in the magma, not directly at least. So it seems as though there's not a direct connection with oxidation state from these data. In this paper, we've used this recent oxybarometer that many of you will know. That's from Bob Laux, published it in Journal of Petrology a couple of years ago. And this is a really useful oxybarometer because it gives us a sense of what the oxidation state actually is in magmas, porphyry magmas. The traditional methods for estimating oxidation state aren't really that useful to us because ilmenite magnetite pairs often get destroyed by alteration. So we have these zircons, they're resistant to alteration. And yeah, so we estimate FO2 and you can see that the oxidation state doesn't change. The log FO2 decreases, but it decreases pretty much parallel to redox buffers, so that there's no change in oxidation state in the resolution magmas. And what that demonstrates is that the cerium anomaly, the increase in cerium anomaly that we just saw in the previous slide, that can't be controlled by changes in melt oxidation state because it seems as though oxidation state is not changing. And so what we did in collaboration with some colleagues at the museum here, we did some modeling. We took I won't go into it in detail. I encourage you to read the paper. And we did some modeling of the zircon chemistry, the cerium anomaly. And what we found actually was one of the strongest controls on cerium anomaly in zircon was temperature. So as you decrease temperature, it causes cerium 4+, the oxidized species of cerium, to become extremely compatible in zircon. It gets more compatible as temperature decreases. And that almost alone can explain most of the variation in cerium anomaly that you see in zircon. And that's what's shown here on this plot, the same increase in cerium anomaly we saw from the previous 2 slides ago, and this time with a model laid over the top, which was run at a fixed oxidation state and a fixed melt chemistry, melt cerium neodymium ratio. And you can see that it matches the data quite nicely. So there's no oxidation required to explain this nearly order of magnitude increase in the cerium anomaly, in a resolution at least. And the final thing I'll say on this, I think it's the final thing I'll say on this paper, is we applied the same models as zircons from some better constrained volcanic rocks. So I have the 2 examples here from quite oxidized systems, the Kneeling Nun Tuff and in Nevada, and in New Mexico, I believe, and the Highland Range volcanics in Nevada. And you can see that, so we have the green line on this plot here represents the model just varying temperature and keeping oxidation state fairly fixed. And you can see that, so we do show an increase in which matches part of the data, an increase in the cerium anomaly as temperature decreases. But then there are these very high values of cerium over neodymium, which only occur at very low temperature. And these very high values, you can't reach those by just cooling alone. You need another process to explain how this ratio of cerium and neodymium in zircon can get so high. And what we've argued is similar to the europium argument I gave before, that actually Titanite is having an impact again. So in both of these volcanic systems, we have Titanite, which crystallizes at quite a late stage, about 750 degrees onwards, something like that. And what Titanite does is it has an impact on the ratio, on the cerium neodymium ratio of the melt. Just like before, it has an impact on the europium anomaly in the melt. It also affects this parameter, cerium over neodymium, in the melt. And when you incorporate that into the models, that's the red line there, you can see that in a very short space of time, we're able to get to some very high values of cerium over neodymium. So we think the cerium anomaly is mostly controlled by temperature. And at a late stage, you can have an upgrade, a bump in the cerium anomaly by co-crystallizing titanite. Oh yeah, finally, just to reiterate the point that oxidation state really isn't required in this model. I have 2 systems here, the Kneeling Nun Tuff that I showed a second ago on the left-hand side, and then the Pinatubo dacite from 1991 on the right-hand side. The reason I've chosen these is because they both have from what we can gather, the same oxidation state, more or less. They're about FMQ, just over FMQ plus 2. So they're similarly oxidized. And yet you can see that the annealing non-tuff has very different cerium anomaly to the Pinatubo dacite, which has much lower cerium neodymium ratios. And the difference between these two, or one of the differences at least, is that the Pinatubo dacite has no titanite in it. So it doesn't have the opportunity to have this late stage increase in cerium over neodymium. Okay, I think that's everything I have to say about this bit. So next slide, please. Okay, so there's been some suggestion in the literature about that we can use the magnitude of the europium anomaly to estimate something about the grade of a deposit. So that's the suggestion here, that you can see that the tonnage of a deposit, rather than the grade, the tonnage increases as the europium anomaly in zircon increases. So I think that's probably quite unlikely. And I think the main reason for that is that in a magma system, there's really no benefit for fertility, in terms of metal concentration. There's really no benefit to being very, very oxidized. So people argue that being quite oxidized is important because you have to mostly have sulfur as 6+, oxidized sulfur, not sulfide, which would saturate and remove metals. So we want to be quite oxidized and not have that process take place in abundance. But really that transition from sulfide to sulfate happens over a very narrow window of FO2, as I'm showing on these two plots here. And once you're at the point where most of the sulfur is present in this oxidized sulfate species, there really is no benefit in terms of metallogeny. There's no benefit to being additionally oxidized. So there seems to be no reason why the increasing oxidation state would affect the tonnage of a deposit. And finally, just to demonstrate this, I have two deposits here that are quite different to each other from Oyu Tolgoi, the Heruga and the Hugo North and Hugo Dummit South deposit. And so I have data from both of them. And really this plot is just to show that in terms of oxidation state, there really is no difference between Heruga, which is in the blue symbols here, and Hugo Dummit. So they're similarly oxidized, and yet the tonnage and particularly the grade of those two deposits are really quite different to each other. So clearly being similarly oxidized wasn't a factor that had an impact, or not directly had an impact on the formation of those two different porphyry deposits. Okay, so I won't dwell on these because I'm I took for half an hour and I probably took for longer, but these are the key points anyway, that europium and cerium anomalies are affected by a complex set of factors that include oxidation, but are not exclusive to oxidation. And oxidation state may not actually have an important role in controlling fertility and metal forming potential. All right, so for the final bit, I'll talk about apatite. Now, I won't go into this too much, why apatite is useful as a mineral indicator, but suffice it to say that it's an abundant mineral. You can get hydrothermal and igneous varieties, lots of trace element substitutions. So it's tracking a lot of things about the melt or the hydrothermal fluid. But the problem is you can actually destroy it quite easily or reset its chemistry by interaction with new melts or new fluids. So it's a useful mineral indicator, but it's not perfect by any means. So here's some results, again, from Chetan Nathwani, a paper that he and I wrote a few years ago now. And just to reiterate this, what I said at the beginning about this deep crustal fractionation, and then shallow crustal in situ crystallization. Chetan had some apatites from volcanic rocks in central Chile, and he showed that the strontium-yttrium ratio of those apatites, so here's using magnesium as an index of fractionation. So as you go from high magnesium to low magnesium, that's basically evolution. So you're going from more primitive high magnesium to more evolved low magnesium. So right to left, that's how you read these plots. And there were three different trends in terms of apatite data on this particular plot, strontium-yttrium versus magnesium. There was one that started at a low strontium-yttrium, one that started at a middle sort of strontium-yttrium, and one that started at a much higher strontium. And what we realized, and we were able to model, is that to get to the starting points of each of those, so I'm now looking at B here on the bottom left, the bottom plot. So if you start from the most primitive apatite, you can get to the starting composition of all of the other, of each of these trends by deep crustal fractional crystallization. Now, you're not generating any apatite during this process. It's unseen by apatite, or if you are, you're leaving that apatite behind in the crust, so you're not seeing it in the rocks at the surface. But you have this process that's changing the starting composition, if you like, for the different magmas. And then when you look at when you model the crystallization of apatite with the other phases that you find in those volcanic rocks, you can see that you're able to actually reproduce those trends just by in situ crystallization of the phenocryst essentially in those samples. But a really important bit here is that the sample that Chetan had that pretty much had the lowest strontium yttrium in apatite actually is from a rock that has the highest strontium yttrium ratio. So that's the Lacopa rhyolite, which has an extremely high strontium yttrium ratio, suggesting something about the fractionation in the deep crust. But the apatites in that rock have very low strontium yttrium. And the reason for that is they've co-crystallized with lots of plagioclase, and the plagioclase has removed the strontium from the melt, but it's not changed the bulk composition of that magma, because you still have that plagioclase present in the rock. So that's something for those people interpreting mineral chemistry. It's worth remembering that the bulk magma can have an effect, but really these minerals are growing from the residual melt. Depending on the timing and the other phases that crystallize, that has a huge impact. Okay, so I'll run through, just for the last bit of the talk, some results on hydrothermal apatites from Oyu Tolgoi. I won't say too much on this slide. This is a cross-section of this is the Heruga deposit, I think, on the right-hand side. Or maybe it's Hugo, I can't quite remember. But we have two deposits here. As I showed in the previous slide, we have a very high-grade Hugo North and Hugo South deposits, and then a much lower-grade Heruga deposit, which is in the same trend, the same age, similar magma chemistry, and also associated with this kind of pink quartz monzonite intrusion here, but quite different in terms of their grade anyway. So we noticed that there were two different types of apatites in these. When we looked at Heruga and Hugo Dummit, there were two main textural varieties. There was this magnetite-associated apatite, which we call MAP, which I don't really love, but anyway, maybe we'll change that when we publish the paper. And this MAP, magnetite-associated, only really occurred in the least altered rocks, a very weak K-silicate alteration, and very, obviously, therefore, very low copper grades. And mostly in Heruga, where the alteration is less than 10, but also in some coeval volcanic rocks. So that's the MAP. Next slide. And you can see an example here of these apatites in not a fresh rock, but not a super altered rock associated with magnetite. That's why we call it MAP. Okay, and then there was another textural type of apatite that we called SAP, and that was sulfide-associated apatite. And this was found in much more strongly altered rocks. So you can see an example of this in the bottom right here. This is sort of brick red K-silicate with a sericitic overprint alteration in the quartz monzonite from Hugo Dummit. And often this alteration is associated with very high copper grades, so up to sort of 2.5 weight% copper, which is astonishingly high. And if we go to the next slide, I think we can see an example of what that apatite looks like in thin sections. This is a very strongly altered rock, quartz case bar and sericite ground mass. We have the apatites there, and then you can see we have chalcopyrite actually growing along cracks in the apatite, intimately associated with that apatite. So clearly the fluid that deposited the chalcopyrite had to have had an effect. It's in a local mineral assemblage, I suppose, with the apatite. So our interpretation was that these apatites might be reflecting something about the chemistry of the fluid that deposited the mineralizing fluid, essentially, the fluid that deposited the copper. You can see here an example from a lower grade but altered rock from Heruga, where we see a sort of mafic replacement assemblage of, again, pyrite associated with apatite, but also chlorite and rutile. So that's the sulfide, SAP, sulfide-associated apatite. So I won't talk about the MAP too much, just to say that there are geochemical differences between these two different types of apatite. The sulfide-associated hydrothermal, we're going to call it hydrothermal apatite, has a flat rare earth pattern, and there's really no difference between Heruga and Hugo Dummit in terms of the rare earth element chemistry anyway. Whereas these, what I'm going to call igneous MAP or magnetite-associated apatites, firstly, they have rare earth patterns that are much more similar to median igneous apatites that we collected from the literature, and they're quite different to these hydrothermal apatites. They have much more depleted heavy rare earths, so much more sloping rare earth patterns. And so I just put this up just to say that this can provide a useful basis to distinguish between these two different igneous and hydrothermal apatites. So lower values of lanthanum, samarium, and lanthanum ytterbium are typical of these hydrothermal apatites that have flat rare earth patterns. And as lanthanum ytterbium, lanthanum samarium get higher, that's reflecting a more igneous signature. So you can use that as a distinction. Okay, so I'm only going to talk about the SAP going forward now. So this is that example again, showing the intimate association with chalcopyrite, and to what extent are they recording the ore-forming fluid chemistry. So there were not many chemical differences between Heruga and Hugo-Dummett in terms of these hydrothermal apatites. But one of the big ones was the concentration of divalent cations, so particularly manganese, but also iron. In the Hugo-Dummett, so the high-grade Hugo-Dummett deposit, that's in red here, had much higher values of manganese and iron in those apatites compared to the Heruga deposit, hydrothermal apatites from which had much lower manganese and iron. And you can see here that, so I've plotted this is the copper concentration of the rock. So we have the whole rock chemistry done on these samples. And this is just kind of like the local copper grade, if you like, along the x-axis. And on the y-axis here, this is the manganese content of the apatites. And you can see that as the rocks get progressively more copper in them, those rocks are associated with apatites that have a much higher manganese value. So in general, you can see that the Hugo-Dummett deposit, they have those higher manganese values, but you can see actually the most copper-rich rock from Heruga also is associated with the highest manganese values in apatite. So even in the deposit that's low grade, locally where the grade is higher, you get this particular high manganese apatite in the hydrothermal apatites. So what we thought we'd do is, rather than characterize by Hugo-Dummett or Heruga, we would characterize these rocks based on the local copper concentration. So that's the x-axis here. We're going to reassign that. And this is the result of that. So the colors in here represent the copper concentration of the rock, but the plot is showing the chemistry of the apatite. So the pale pink colors, that's low copper grade, and the darker red and then eventually black colors, that's much higher copper grade in the local copper grade in the rock. And what you can see is firstly that manganese and apatite broadly correlate with each other. So manganese and iron in apatite broadly correlate. So high manganese equals high iron in general. And you can also see that all of the apatites from rocks that had a high copper concentration, they seem to plot at these high manganese and iron values. There's a lot of data from the low copper concentration rocks also falling behind there. You can see there's some pale symbols that have high manganese and iron. But the important point is that there are no apatites from high-grade rocks that have, there are no apatites from high-grade rocks that have low manganese and iron. So there's like a threshold, if you like, of about 1,000 ppm iron and about 2,000 ppm manganese, above which we have a mix of high-grade and low-grade rocks, but below which we only have low-grade rocks. So it seems as though that high manganese and iron seems to be a signature of particularly high copper grades. And so the question is, well, is this unique to porphyry systems in general, these signatures? So what I have here is at the time when I did my PhD, this is all the apatite data that existed in the literature. There is a lot more now. But these are sort of a mix of igneous and hydrothermal apatites all on the same plot. The point was, if you were looking at stream sediments or something like that, and you wanted to know whether or not, is this signature unique to porphyry systems? You can see that there are apatites from the literature that also have high manganese, but those high, and they're particularly from S-type granites, they have high manganese values, but they're also accompanied by low strontium values. Whereas the hydrothermal apatites from Oyu Tolgoi, they have both high manganese and high strontium values. So those dark points there define a cluster, define a field, which seems to be unique to porphyry copper deposits, and particularly high-grade porphyry copper deposits. And you can see broadly the same thing here, except we've swapped the x-axis of these plots. Rather than strontium, this is now europium star in apatite, which is also higher compared to the S-type granites apatites, the open symbols, which are much lower. And the final thing, so we're currently working to write this up. I think we'll submit this soon, hopefully. So this is a slightly old interpretation of this, but the final thing I'll note is that we noticed that there was a relationship between the chlorine concentration of our apatites and the manganese and iron concentration as well. So as you increase the chlorine concentration in general, that tends to be associated with apatites that have a higher manganese and iron. And when I originally made this presentation a few years ago, our interpretation was that perhaps something to do with the salinity of the fluid is affecting the apatite chemistry, both in terms of chlorine. So obviously more saline fluids, you would tend to get higher chlorine concentrations in hydrothermal apatites, but also because chlorine acts as a ligand for metals, in fluids, it's a great ligand for divalent cations, which can make chloride complexes. So those chlorine-rich fluids will be more likely to be able to carry manganese and iron, but also copper. So there's been experimental work more recently that's shown, and actually from a while ago, showing that the salinity of the fluid has a direct effect on the ability of that fluid to carry copper, but it would also affect the manganese and iron. So maybe there's some connection between these high-grade rocks and these manganese and iron-rich apatites. Maybe they're reflecting a process which is to do with the salinity of the fluid. So since we came to that conclusion, we've modified it slightly. And I won't say too much about it now because we're writing it up at the moment, but I suppose I'll say watch this space. There's hopefully a paper coming out at some point soon. So if you go to the next slide, I think that's the end of my talk. Yep, I've talked for quite a while now. But anyway, I hope that's been interesting. Just a sort of whistle-stop tour of some of the work we've been doing on zircon and apatite. And I'm happy to take any questions if there are any.
Thank you, Matt. This was a great presentation. I learned a lot today. So maybe I can go ahead. Matt, did you also look at fluorine contents?
Fluorine contents in apatite?
Mm-hmm.
Yeah, we did. So as you may be aware, fluorine is actually really difficult to analyze in apatite. Mm-hmm. Typically, we do it by electron probe. The only really fail-safe way of doing it is by SIMS. But we did look at fluorine concentrations, yep. And we made an effort to make, the problem is that when you apply an electron beam to an apatite, the fluorine migrates towards the beam, and so you end up with a higher fluorine value than is actually there. So we measured fluorine, and you don't have the same problem with chlorine, of course. The fluorine values were all below the stoichiometric limit for fluorine and apatite, which is good, obviously. You don't want the values to be higher. I wouldn't want to lean on the fluorine data too much though, because it's as I say, analytically, it's a bit fraught. Yeah, I think the chlorine data is probably, but in general, as chlorine concentrations are higher in apatite, fluorine concentrations are lower. There's not really a huge OH component in most of these apatites. So it's really an inverse relationship between fluorine and chlorine.
Mm-hmm. Okay. And all of your measurements, they were by microprobe, or did you also use laser ablation?
Oh yeah, good point. No, I didn't say that. Yeah, so all of the halogen measurements were by microprobe, but all of the trace elements obviously were measured by laser ablation. So we did microprobe work first, and then we did the laser ablation on the same spots that we've done the microprobe. And we made an effort to sort of cross-calibrate. So we analyzed manganese by electron microprobe and also by laser ablation, and the correlation there was really nice. So I think we're quite confident that we're sort of analyzing the same spots. And yeah.
Said would like to know what is the relationship between zircon and ilmenite, because zircon normally is found with ilmenite.
Yeah, so that's a good question, Said. So in general, we find ilmenite more typically associated with slightly more reduced magmas. So you're right that certainly zircon can co-crystallize with ilmenite. Most porphyry magmas, there's not a huge amount of ilmenite around because they tend to be a bit more oxidized. Typically, the titanium species we'd have would be, well, we have titanomagnetite often, but we also have titanite. So in general, no, in porphyry systems, you don't have an awful lot of ilmenite. And in any case, the kind of elements that go into ilmenite don't really also go into zircon. I mean, obviously titanium does, but niobium and tantalum maybe also in zircon. So it might have an impact on the zircon chemistry, yeah, if it co-crystallized.
Hi, hello. Thanks, Matt, for the amazing speech. Really awesome. I got a question because you were talking about the Oyu-Tolgoi, which is Paleozoic. And I wonder if the younger deposits like Chilean, Ecuadorian, or North American show the same geochemical characteristic that you described. Thanks for answering.
Yeah, that's a great question. So the Chilean systems tend to be a little bit different, but I don't think that's to do necessarily with their age. I think that's more because, as you'll know, most of the Chilean systems are copper moly systems, whereas Oyu-Tolgoi is a copper gold system, kind of a more alkalic magma in general. So there are differences between, say, Oyu-Tolgoi and Chuquicamata or somewhere like that. But that's mostly to do with the difference in the magma chemistry and not the age. But if there was, an alkalic porphyry system in Chile, which I'm sure exists, I would expect to see the same kind of characteristics. And in any case, the high cerium anomalies, the high europium anomalies that have been the focus of my zircon stuff, they are high also in the Miocene and Eocene Chilean deposits, and in the Paleozoic. It's the same. Actually, Oyu Tolgoi has some of the, and Apatite as well, have some of the highest europium star values for a complicated reason, but it's nothing to do with the age of those deposits. It's to do with the chemistry of the magma. So yes, in answer to your question, you would expect to see the same thing in younger magmas if the melt chemistry was the same.
Great, thanks.
You can ask John Barry to please unmute and ask your question.
Hello, good morning. Thank you. Great talk, Matt. Just from a practical exploration perspective, do you see this as being just as equally valuable in grassroots exploration as in sort of established camps, would be particularly with regard to manganese and the apatites?
Yeah, so I can give you my, I'm not someone who works, I've worked with industry, but I've never worked for industry, and I've never done any exploration on my own. But I've had lots of conversations with people about this, obviously, and it was funded by Rio Tinto, my PhD work. So I can give you for what it's worth, I can give you my take on that. Well, I'll start with this. You asked about apatite, but I'll start with zircon. What zircon is reflecting is magma chemistry. But as I showed at Oyu Tolgoi, the magma chemistry in the very high grade Hugo Dummett system and the much lower grade Heruga system is basically identical. There's no difference really in the magma chemistry between those two. So there seems to be some other process which is controlling them. So what that means for zircon is it probably would be more useful at a grassroots stage. Let's say if you're doing a big regional exploration campaign, you could look for zircons in outcropping granitoids or other volcanic rocks, other igneous rocks, also in stream sediments. And if you had a big compilation of zircon data, both geochemical and geochronological, then you could use the geochron and the geochem in concert with each other to identify the particular magmatic epochs that would be useful to you. So we know, if you went to Chile, for example, and you did that, you would find that there'd be high europium star values or whatever associated with an Eocene age and maybe a slightly older Paleocene age as well. So it would be useful for you at that scale in picking the useful magmatic epochs, the windows, and then you can use your geological mapping to constrain further. Certainly if you're using stream sediments and you find there's a certain catchment that just has loads of these particular high europium star grains, you might want to look up that catchment. That would be a good idea. Now, in terms of the apatite, yeah, that's a bit tricky. I suppose in general, if you see high manganese, high iron apatites that also have high chlorine, and there's a couple of other parameters which we'll get around to publishing that paper eventually. That seems to be a uniquely porphyry signature. So whereas in zircon, the high europium and cerium anomalies are not unique to porphyry systems, you also find that in barren, unmineralized systems. So it would be an indicator of the right kind of magma, but not necessarily the presence or absence of a deposit. Whereas with the apatite chemistry, I think that would be firstly an indicator that you had a hydrothermal system, because it seems to be a hydrothermal signature. And if it's high manganese and iron, it would be an indicator of a particularly interesting hydrothermal system. Now, I would say that you'll have noticed my apatites that had high manganese and iron were intergrown with chalcopyrite and bornite as well in some cases. So if you were drilling, for example, and you wouldn't need to go to the point of doing laser ablation on an apatite because you have the chalcopyrite, you found the deposit. Where this would be more useful, I think, is if you have a partially eroded deposit, which is then covered, blind, and you're sampling in stream sediments, and you're able to detect that signature, then I think that's where it would be more useful. So if you wanted to do that on a district scale, that would be, but that might be more a camp scale kind of thing. And the other interesting point about this is if it's something to do with the chemistry of the fluid that's affecting, that's different between high grade and low grade systems, whatever that might be, then you might expect to see that washed distally outwards into the green rock environments, the propylitic environment. So if high manganese and iron is interesting, then you might expect to see that represented in chlorite or epidote or calcite or whatever, with a bit much bigger distal footprint. So that's I think where my work fits into that. So apologies, I can't give you a more comprehensive answer because I don't use these tools in exploration, but that would be my takeaway anyway.
Thank you very much for that. Just one last question. Where is it possible to get this analysis done on these zircons and apatites?
Well, I mean, we do them commercially at the Natural History Museum.
Okay, all right.
Yeah. So yeah, if you wanted to send an email, I can put you in contact with people.
Thank you very much.
No worries.
Oh, thanks, Matt, for that great discussion, and thank you all for the questions. There's one question from Xin Qiao. Xin Qiao wants to know what is the most difference between apatite magnetite with apatite sulfide? Are they present in different hydrothermal condition, oxide state?
Yeah, okay, so that's a good question. So I think the main difference between the sort of magnetite apatite and the sulfide apatite, well, obviously there's a textural difference. They're found in different rocks. The magnetite apatite, the M-apps, as I was calling them, you don't find those in very strongly altered rocks. That's probably an igneous signature. So I think they're igneous in origin, or a very high temperature hydrothermal overprint that's kind of basically igneous. Whereas the sulfide apatite, we find that more closely associated with altered rocks, case silicate, potassic altered, but also particularly sericitically altered rocks. And so, yeah, and perhaps some of the difference that we're seeing in the chemistry of those sulfide-associated apatites might be reflecting something to do with the different hydrothermal conditions in those systems. I think that's probably fair. In terms of oxidation state, well, yeah, I mean, there will be a difference in oxidation state between the fluid and the melt, but I don't think manganese and iron are being controlled. So those are, if I've understood your question properly, manganese and iron are also redox sensitive elements. So iron 3+, for example, can exist as well as iron 2+. But we don't think that the variation in manganese and iron that we're seeing is related to redox, because we see it with other non-redox sensitive elements as well, like strontium and vanadium and lead as well. So yes, they're redox sensitive elements, but they're probably not reflecting a change in redox state in the S-app as well, is what we see.
Okay, so Mate wants to know, which one do you prefer? The apatite found in the S-type granite, or the one found in the I-type granite?
Yeah, I'm not sure I quite understand the question. It seems to be which granites most prefer.
I'm guessing in terms of maybe mineralization, which sort of apatite would you prefer? Is it the one you find in the S-type granites or in the I-type granites?
Well, yes. So typically we don't get porphyry copper systems associated with S-type granites. They're typically I-type granites, although, a bit of uncertainty there. But yeah, generally porphyry magmas, generally speaking, are associated with oxidized systems and are typically associated with I-type granites there. I mean, there is a chemical difference between apatites, S-type and I-type systems, as I showed on one of the previous plots there. But generally, in terms of mineralization, when porphyry mineralization, porphyry copper, we're mostly interested in the I-type systems.
And then the last one from Mark. Okay, so Mark wants to know, do you have any data from the older division? I'm guessing that's a division north-southwest systems, the North Parkes or North?
Yeah, so New South Wales. So no, it's a short answer. I don't have any apatite data from North Parkes or Cadia or any of those systems. I'm not sure if it's published, although that would be interesting. I think I see where you're going with this, in as much as the picture I showed of that very brick red alteration that you see at Oyu-Tolgoi is very similar to some of the alteration that you get in North Parkes. And I suppose, therefore, you would expect to see a similar thing at North Parkes than you see at Oyu-Tolgoi, but I haven't tested that. Identical, yeah, exactly. Yeah, it looks like it would be potassic alteration, brick red, you think case bar, but a lot of it's just hematite. There doesn't have to be a lot of case bar in the rock actually to have that alteration. And in fact, often there's a sericitic overprint, which is kind of hiding in between the grains. Yeah, exactly. Hematite wash. Okay. All
right. I think, we do not have more questions in the chat. And thank you, Matt, for that interesting talk. And thanks everyone for tuning in. We have one last talk for the season, and that will be at 5 o'clock GMT. So please do log in and say goodbye to season 5 of Ore Deposits Hub. With that, it is goodbye from Ore Deposits Hub, and keep safe and see you in a few minutes time. Bye.